Content of today's lecture: introduction, methods to find voltage regulation, direct loading method, synchronous impedance method, Ampere turn method, and force theory. Okay. So first of all, introduction about voltage regulation. So first of all, the definition of voltage regulation. So the rise in voltage at the terminals when load is reduced from full load rated value to zero by and keeping speed and field current constant. Okay, so if we keep the speed and field current constant at that time, the rise in terminal voltage when full load is removed is known as the voltage regulation. Okay, so we assume that we have alternator. This alternator operates on full load condition. Okay, and suddenly we are removing this full load, so this alternator operates on no load condition. In this situation, what is the condition we have to keep constant, that is the speed and field current or field excitation. Okay, so speed and field excitation we have to keep constant. Okay, so by keeping the field current and speed constant and we are removing the load, okay, at that time whatever rise in voltage, terminal voltage, that is known as the voltage regulation. Okay, another definition is the rise in voltage when full load is removed divided by the rated terminal voltage when speed and field excitation remains same. Okay, the condition we have to keep in mind, that is the speed and field excitation must remain constant. Okay, in this situation, whatever rise in the voltage when we are removing the full load, that is known as the voltage regulation. So in equation form, percentage voltage regulation is equal to E0 minus V divided by V multiplied by 100. 100 is for percentage. Okay, so percentage voltage regulation is E0. E0, that is the no load terminal voltage, minus V. V is the full load terminal voltage or rated terminal voltage divided by rated terminal voltage. Okay, so percentage voltage regulation is equal to E0 minus V divided by V into 100. Okay, some basic introduction or related to the voltage regulation. The value of the voltage regulation not only depends on load current but also on the power factor of the load. Okay, so this voltage regulation depends on two factors. It depends on load current as well as the power factor of the load. Okay, so power factor of load, that means it depends on the types of load. We have mainly three types of load: resistive load, inductive load, and capacitive load. Okay, so resistive load has unity power factor, inductive load has lagging power factor, and capacitive load has leading power factor. Okay, so this voltage regulation depends on load current, that is the magnitude of load. So load, it depends on load current as well as the types of load, that is the power factor of the load. For lagging and unity power factor conditions, there is always drop in terminal voltage, hence regulation values are always positive. Okay, if the load connected to alternator is of lagging type, that means the inductive load, and unity power factor, that means the resistive load. So when the load is of resistive and inductive, at that time there is some voltage drop in the terminal, or we can say that the voltage drops in terminal voltage. Hence, according to this formula, what happens? The E0 minus V divided by the voltage regulation is always positive. Okay, while for leading capacitive load condition, so for capacitive load condition, what happens? The terminal voltage increases as load current increases. Okay, in this condition situation is different. It is not looks like inductive and resistive load. In capacitive load condition, when load increases, at that time load current increases, and due to it the terminal voltage increases. Okay, so here what happens, as the terminal voltage increases, what that means E0 minus V, this condition becomes negative. Okay, so for capacitive load condition, the voltage regulation is negative. The relationship between load current and terminal voltage is called load characteristics of alternator. Okay, so load characteristics of alternator is the relationship between load current and terminal voltage. So this is the brief introduction about the voltage regulation. Now the different methods, that is the Methods to find the voltage regulation. Okay, so we have mainly two methods: direct method and indirect method. Okay, in direct method, physical load is directly connected with the alternator, whereas in indirect method, physical load is not connected. Okay, so in direct method we have a direct loading method, whereas in indirect method we have a synchronous impedance method, ampere turn method, and ZPF method, zero power factor method. So these are the three methods which are included in the indirect method. Okay, understood? We have mainly two methods: direct method and indirect method. In direct method, physical load is connected to alternator, whereas in indirect method, physical load is not connected. Okay, understood the difference between these two: direct method and indirect method. Okay, now today we discuss about the synchronous impedance method. Okay, it is the indirect method. That means the load is not connected to physical load is not connected to alternator, but we are creating such type of full load condition without connecting a physical load. Okay, so it is based on the concept of replacing the effect of armature reaction with an imaginary reactance. Okay, on this concept this method works. Okay, so this method is also known as the EMF method. Okay, synchronous impedance method is also known as EMF method. So in this EMF method, what happens? The voltage drop due to the armature resistance and drop due to synchronous reactance is considered. Okay, so when current is flowing through armature winding, at that time IARA drop occurs, as well as due to the synchronous reactance some drop occurs. Okay, so in this method we are considering two drop, that is the IARA drop and IA excess drop. Both drops are EMF quantities. Okay, the unit is the voltage. Okay, so the impedance of armature winding is expressed as ZS is equal to RA plus J XS ohm per phase. This is the formula of impedance of armature winding. Okay, so this impedance of armature winding is nothing but the synchronous impedance of an alternator, and since the drop due to synchronous impedance considered, this method is called synchronous impedance method. Why this method is known as synchronous impedance method? Because in this method the drop due to the armature resistance and synchronous reactance is considered. Okay, and if we combine this armature resistance and synchronous reactance, then it becomes the synchronous impedance ZS. So ZS is equal to RA plus JXS. Okay, so in this method drop due to the synchronous impedance is considered. That's why this method is called the synchronous impedance method. This method is also called pessimistic method. Why? Because the voltage regulation obtained by this method is more than the actual value. Okay, so in this method, if we calculate the voltage regulation of alternator by synchronous impedance method, then we are getting more voltage regulation compared to the actual value. That's why this method is known as the pessimistic method. Okay, so the EMF method, this EMF method, or we can say that the synchronous impedance method requires following data to determine the voltage regulation. Okay, so if we want to find the voltage regulation of alternator, we need the armature resistance per phase, then open circuit characteristics, which is also known as OCC, and third one is the short circuit characteristics, that is the SCC. Okay, so these three data are required: armature resistance per phase, open circuit characteristics, and short circuit characteristics. Okay, now measurement of synchronous impedance. How can we measure the synchronous impedance? Okay, because this is the synchronous impedance method, so we have to measure the synchronous impedance of the alternator. Okay, so the measurement of synchronous impedance is done by the following methods. Okay, we have different methods to measure the synchronous impedance of alternator. That is the DC resistance test, open circuit test, and short circuit test. So using these methods we can measure the synchronous impedance. Okay, so generally the DC resistance test is used to measure the synchronous impedance. It is assumed that alternator is star connected with DC field winding open. Okay, in this diagram we assume that the alternator is star connected. Okay, this is the armature winding of alternator, and it is a star connected with DC field winding open. This is the field winding. Okay, so this field winding is kept open, whereas this is the armature winding. It is the star connected winding. Okay, now in this DC resistance state, what happens? It measures the DC resistance between each pair of terminals, either by using an ammeter voltmeter meter or by using the Wheatstone bridge. Okay, so in this, what happens? This ammeter is connected here. In between these two phases, the voltmeter is connected. Okay, so in between these two phases, the voltage is measured, and in this current is measured. So V by I, we can find the resistance. Okay, so the average value of three sets of resistance is taken as RT, and this RT is divided by 2 to obtain the value of DC resistance per phase. Okay, since the effective AC resistance is larger than the DC resistance due to the screen effect, therefore the effective AC resistance per phase is obtained by multiplying the DC resistance by a factor of 1.20 to 1.75 depending on the size of machine. Typical value is the 1.25. Okay, so what we have to do? We have to measure the DC resistance between each pair of terminals. So here it is these two terminal, then measure the resistance between these two terminals, then measure the resistance between these two terminals. Okay, so this is the one pair of terminal, this is the second pair of terminals, and this is the third pair of terminals. Okay, so after measuring, what we have to do? We have to take the average value of these three readings, that is known as the RT. Okay, so here is the R1 in between these two terminals, then it is the R2, and in between these it is the R3. Okay, so R1, R2 and R3. Okay, so this is the average of the three sets of resistance that is taken as RT. Now this RT is divided by 2. Okay, which gives the DC resistance per phase. Okay, so DC resistance per phase is equal to RT by 2. Now what happened? Due to skin effect, the AC resistance is greater than the DC resistance. Okay, so what we have to do? We have to multiply DC resistance by a factor of 1.20 to 1.75. Generally we are using 1.25. Okay, so AC resistance is equal to 1.25 of the DC resistance. Okay, so what we have to do? We have to give DC supply to this armature winding and then measure the voltage and current in between each pair of terminal. Okay, so now the DC by using DC resistance test, we can measure the AC resistance, then open circuit characteristics. Okay, second data required is the open circuit characteristics. Now this is the circuit diagram of the synchronous impedance method. Okay, this is the alternator, armature winding of alternator. This is the field winding of alternator. This is the prime mover in which the DC shunt motor is used. Okay, this is the field winding of DC shunt motor in which the rheostat is connected in series. So with the help of field control method, we can adjust or we can control the speed of DC shunt motor. Okay, DC shunt motor and this alternator both are mechanically coupled. Okay, shaft of DC shunt motor and shaft of alternator are mechanically coupled. So if the DC shunt motor operates on 1400 RPM, then this alternator also operates on 1400 RPM. This voltmeter will measure the terminal voltage. This ammeter measures the load current. Okay, this is the field winding and DC supply is given to this field winding to excite the for giving the excitation. Okay, and this is the rheostat connected in series with the field winding. So this ammeter measures the field current of alternator. Okay, so this is the prime mover and this portion is the alternator. Okay, okay, to obtain the open circuit characteristics, we have to keep the switch as open. Okay, this is the TPST switch. We have to keep this TPST switch as open. Okay, now what happens when switch is open? At that time, by keeping this switch as open, we have to switch on the DC supply, and with the help uh, by 3-point DC shunt starter, we have to run the DC shunt motor. Okay, after running the DC shunt motor, we have to adjust the speed of DC shunt motor with the help of field control method. Okay, so what we have to do, we have to maintain the rated speed of DC shunt motor. Okay, so at that time what happened, this alternator also operates on the rated speed. Okay, in this situation what we have to do, we have to keep the maximum resistance in the field of alternator. Okay, so at that time this ammeter measures the minimum reading nearly equal to 0. Okay, now at that time zero field current, we have to measure this open circuit voltage. Okay, so in this which are the reading in observation table, we have to note down the reading of open circuit voltage. This voltmeter measures the open circuit voltage, and this ammeter measures the field current. So it is the VOC and this is the IF. So we have to note down the reading of VOC, that is the open circuit voltage, and IF, that is the field current. Okay, so at zero field current, we have to measure the open circuit voltage. Now gradually we have to cut out the resistance from the field circuit of alternator, and step by step we are cutting out the resistance, and each and every step we have to measure the field current of alternator, and for that field current of alternator we have to measure the open circuit voltage. Okay, so 10 to 15 readings we have to take from 0 to maximum field current. Okay, so we have to adjust the field current up to the such value that this voltmeter measures the rated terminal voltage, rated open circuit terminal voltage. Okay, so now we have a VOC and we have a IF. Okay, so with the help of these two reading, we have to draw a graph. Okay, on x-axis we have to take the field current, on y-axis we have to take the open circuit voltage VOC. Okay, and if we draw the graph, then it looks like this. Okay, this is the x-axis on which we are taking the field current, this is the y-axis on which we are taking the open circuit voltage, and if we draw the graph, then it looks like such figure. Okay, we are getting such type of figure curve. Okay, so this is the open circuit characteristics. Okay, now second characteristics we are required, that is the short circuit characteristics. Okay, so in short circuit characteristics, what we have to keep in mind first, when we are doing the short circuit test, at that time we should keep the maximum resistance in the field of armature. Okay, the value of resistance of this resistor must be a maximum value. So minimum current, that is nearly equal to 0 current, will flow through this field winding. Okay, this is the main thing we have to keep in mind when we are doing a short circuit test. Okay, once again, keep the switch as open, run the DC shunt motor, adjust the speed of DC shunt motor on rated value, so alternator also rotates on the rated speed. Now, and as soon as the resistance is maximum, minimum current will flow, or we can say that nearly equal to 0 current will flow through the field winding of alternator. Now close the switch, close this TPST switch. So what happens, as soon as the switch is closed, the armature winding of alternator becomes short circuited. Okay, now in this situation what happened, this ammeter measures the short circuit current. Okay, and this voltmeter measures the voltage. Okay, and this ammeter measures the field current. Okay, so in short circuit characteristic we need a field current and short circuit current. Okay, So now what happened? Gradually we have to cut out these resistors from the circuit, and each and every step we have to measure the field current and the short circuit current. So it is the IF and it is the ISC. Okay, 10 to 15 readings we have to take. Okay, and we have to adjust the value of rheostat such that this ammeter measures the rated short circuit current. After that we should not cut out the resistance. Okay, if we cut the resistance more, then what happens? More current will flow through the armature winding and it will get damaged, or armature winding will get damaged. Okay, so what we have to do, we have to keep in mind that the rated current must be flow through this armature winding, and more than rated current should not be flow through this armature winding. Okay, so this is the fact we have to keep in mind. Okay, so now we have a field current and we have a ISC, that is the short circuit current. Okay, so with the help of these two, we have to take the field current on x-axis and short circuit current on y-axis, and if we draw the characteristic, then it looks like a straight line. So this characteristics is known as the short circuit characteristics. Short circuit characteristics, that means the relationship between field current and short circuit current, whereas open circuit characteristics is the relationship between field current and open circuit voltage. Okay, so after plotting these open circuit characteristics and short circuit characteristics, okay, what we have to do when the short circuit occurs, okay, when short circuit occurs, at that time whatever voltage generated in the armature winding, that becomes zero to circulate the short circuit current through the armature winding against the impedance, synchronous impedance. Okay, શું થશે? જેવું શોર્ટ સર્કિટ તમે કરશો એટલે જે પણ વોલ્ટેજ જનરેટ થયા હતા એ બધા વોલ્ટેજ જે છે એ વપરાઈ જશે. શામાં વપરાઈ જશે? એ આર્મેચર વાઇન્ડિંગમાં શોર્ટ સર્કિટ કરંટ ફ્લો કરાવવા માટે. કોની અગેન્સ્ટમાં? તો સિંક્રોનસ ઇમ્પિડન્સની અગેન્સ્ટમાં. ઓકે, સો વોટ એવર વોલ્ટેજ જનરેટેડ ઇન ધીસ આર્મેચર વાઇન્ડિંગ, that is used to circulate the short circuit current through the armature winding against synchronous impedance. Okay, so what we can write? We can write the whole open circuit voltage is equal to ZS into ISC, or ISC into ZS. Okay, so ZS is calculated by ZS is equal to open circuit voltage divided by short circuit current. Okay, and that is calculated on the rated value. Okay, so how can we calculate the ZS value? So we have to take the rated field current. On this rated field current we have to measure the, so suppose this point is the rated field current. Okay, so draw one parallel line to y axis from this rated field current which cuts the open circuit characteristics at one point, and from this point we have to draw one parallel line to x axis which cuts the y axis at one point, which gives the rated terminal voltage, that is the VOC rated. Okay, then we have to find the short circuit current. So for the rated field current, okay, for rated field current, measure the short circuit current, that is the rated short circuit current. Okay, so from this graph we have to find the VOC rated and ISC rated. Okay, so after measuring the VOC and ISC, we can calculate the synchronous impedance. ZS is equal to VOC divided by ISC. This VOC is the per phase value. Okay, after getting the synchronous impedance, we can calculate the ZXS, that is the synchronous reactance. Okay, so we have a value of armature resistance that is measured by the DC resistance test. We have a ZS value that is calculated by the graph, from the graph. Okay, so after that we have to calculate the synchronous reactance, that is XS. Okay, so XS is equal to √ ZS square minus RS square using this formula. Okay, Now, how can we calculate the E phase? Okay, or we can say that the E0. So we have a formula for lagging power factor. E0 or E phase is equal to under root V phase cos phi plus IARA whole square plus V phase sin phi plus IA access whole square. Using this formula, we can find the value of no load induced EMF or no load voltage, that is E0 or E phase. Okay, this formula is for lagging power factor. Okay, now for leading power factor, the value of E phase or E0 is under root V phase cos phi plus IARA whole square plus V phase sin phi minus IA access whole square. In leading power factor, just keep in mind that it is minus IA access, whereas in lagging power factor it is a plus IX. This is the difference between these two formula. Okay, so now this is the E phase. Okay, so finally voltage regulation of alternator can be determined by the formula. Voltage regulation is equal to E phase minus V phase divided by V phase, or we can say that E0 minus V divided by V. Okay, and in percentage it is E0 minus V divided by V multiplied by 100. Okay, so all values are the per phase value. That's why here it is written as the E phase minus V phase divided by V phase. Okay, so using this formula we can find the voltage regulation of alternator by synchronous impedance method. Okay, so today we discuss about the synchronous impedance method to find the voltage regulation. This method is known as the pessimistic method because the whatever voltage regulation we are getting in this method, that is more compared to the actual value. That's why it is known as the synchronous impedance. It is known as the pessimistic method. Now, why it is known as the synchronous impedance method? Because the synchronous impedance is calculated from the graph, and using this we can calculate the voltage regulation. That's why it is known as the synchronous impedance method. In this method, physical load is not connected. Okay, so we can easily do the experiment to find the voltage regulation. This is the advantage. Okay, but the major disadvantage is that we cannot find the actual loading condition of alternator because the physical load is not connected here. Okay, and there is no wastage of power. Okay, physical load is not connected, that means there is no wastage of power also. So synchronous impedance method is the method to find the voltage regulation of an alternator, and this method is the indirect method in which physical load is not connected. It is also known as the EMF method. It is also known as the pessimistic method. Okay.